good morning or good afternoon. Let's go ahead and get started and talk a little about triangle congruency. So everything we've been doing up to this point has led us kind of to this moment where we're going to now for the next few days, next couple weeks until the end of the semester, talk about how you prove things are congruent. Now we're going to do that, and as you can see by this essential question that you should get down in your notes, we're going to do that without proving everything. And so what we're going to find is that, yeah, we're going to have this definition for congruency. It's going to talk about having to match all corresponding pieces. But that's ultimately a very unrealistic thing, not just in the realm of math, but like in the realm of real life. It's not often that you have to complete a task and you have all the information to do it. And so at some point you have to make some choices, and some of those choices might be to make reasonable assumptions about the rest of the information that you simply cannot prove. And I'll talk about that in the upcoming notes. So please get the essential questions down. Let's first talk about what it actually means for two figures to be congruent. And so what we can start with is the actual definition of congruency. Now this is something we've dabbled with pretty much all year, so this is kind of just the final word on it, the final version of it. But when you're talking about the congruency or the definition of congruency, what you're saying is that, and it's really a condition, if two figures are going to be congruent, let's see, congruent here. Let's use a symbol just as a reminder. Remember, that's the congruency symbol. So if two figures are congruent, that means all corresponding sides and angles are congruent. Okay? And that's a condition that we cannot get around. So if we had these two triangles below, and they're kind of configured kind of this weird way, just so we can talk about it more fluidly, let's first name these vertices. Remember, algebraically speaking, it doesn't matter how you, I'm sorry, geometrically speaking, it doesn't matter how you name them. You just got to call them something so we can refer to them in the future. So if I'm going to prove these two triangles below are congruent, I have to match all corresponding sides and angles, and I have to know they're congruent too. And so like this side BA, which is kind of like the short side, corresponds to DE. And if I'm going to call these figures congruent, they have to be. BC, the hypotenuse looking thing, has to match and be corresponding and congruent with DC. Let's see, what color? Green. Okay, AC down here has to correspond and be congruent with CE. But it also has to be true about the angles as well. And so these two angles here, which are corresponding, not vertical, remember, they have to be congruent. Let's see, running out of colors here. The angle up here at B has to be corresponding and congruent with the one at D. And the one at A, which I'm not going to mark as right because I don't know if it actually is, has to be corresponding and congruent with E. And this is a burden of proof. If you're going to prove these two triangles are congruent, you have to know all this information. Now, if you do know all this information, or you're supposing that it's true, we can write something called a congruency statement. Now, a congruency statement is nothing more than a statement of the two triangles that shows the corresponding relationship. So what I mean over here, if we call this triangle BAC, please notice the order of BAC starts in the upper left, goes down to A, and then over to C. The congruency statement would make it congruent on the right to triangle DEC. Okay? And the thing to notice here is that BAC on the left follows an order of vertices that DEC imitates, and so that's what we call a congruency statement. All right? And so if we're going to prove BAC is congruent to DEC, the diagram certainly kind of reflects all the information we have to show, but we can also write that out. So if we're going to make a list of all the things we'd have to prove to be true, the first thing we'd have to prove is that BA is congruent to DE, and so the left and right hand sides are corresponding and congruent. We'd also have to prove that AC, a segment, is congruent to CE segment. And then for this final one, we'd have to prove that BC as a segment is congruent to, let's see, CD as a segment. Now, as terms of the angles involved here, again, we're going to name these angles using the typical convention. Okay, so we have angle BCA congruent to angle DCE. The one in the corners, we have angle BAC congruent to angle DCE. Remember that three-letter convention, the middle one has to be the vertice. And then we have angle ABC congruent to angle, let's C, EDC. Okay. Now, if that started to get very tedious, that's important to note because although this is a full definition of congruency, it seems that we don't really need to prove all those pieces. As I aforementioned, maybe that's because it's unrealistic to think that we can get them all, but also at some point enough might be enough. And so we're going to turn our attention in terms of how to prove these to this question. Okay? How much information is really enough? Do I really have to match all 6 corresponding sides and angles? And it turns out the answer is no. And so let's get this statement out here, but then let's proceed in actually explaining why. So the answer to this question is ultimately no. As it turns out, there are 4 triangle congruency shortcuts. And those are what we call theorems. Now remember, theorem is just an idea. It's just the thing out there in geometry that represents a thought, an idea that we can prove or disprove to be true. In other words, if you have shown the right, and we're going to show that this actually only needs 3 pieces of information, the rest can be safely assumed to be true. Okay, so before we get into the bottom part of these notes, I'm going to try to maybe hopefully explain a little bit better like what I mean. So let me move this thing out of the way, and let's look at this website for a second. Now this website, I left the link in the Schoology thing folder, and so you can certainly play with this too if you want. But I'm going to try to kind of explain what I mean. And so you have to kind of picture this triangle ABC. And let's say we don't know all the information. Let's say we just know 3 pieces of the information. The question that we should be obsessed with is whether or not that information is enough information. So for example, if I just select like these 3 sides, and that's all I select, I don't know what the angles are, but I have to create a triangle out of these. And so if you notice, like some of these letters are the same, so I'll attach C to C, and maybe move them up a little bit at an angle. Okay, I'll attach B to B. Let's actually, there we go. B to B, and then I have to make the A's connect. So I don't know what the angles are here, but I do have 3 side lengths, and those 3 side lengths have to form a triangle, and there I have it right there. Now, if you see here, I'm keeping the same 3 side lengths, and I'm going to try to form a triangle as well. Now, these are the same. I'm not going to show you all 3, but if you kind of look at like the AB line, that does match this YQ line, and same is true for the other ones. And so my task is to form a triangle. So what we're going to see here is even though I'm trying intentionally to maybe not form the same triangles I had before, because I'm locking my sides as a length, because I can't move change my side lengths, excuse me, I can only produce the same triangle. So let me do some kind of moving around here, kind of move that into place. It's not going to be perfect, but you can see through a series of transformations, reflection, rotation, and translation, these are going to match up. And so like what this kind of shows is that as long as I keep my sides the same, my angles have to stay the same too. In other words, the triangles are congruent, which means like this right here, side, 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 becomes a viable shortcut. In other words, we don't have to show the angles if we just know the sides. Okay? And this is not true just of this set, but true of other sets too. So let me reset this. So let me unselect these. So let's say I have a side length, and then an angle, and then the next side length. Okay, and so I don't have again the whole triangle locked into place, but I do have parts of it. So I have what's referred to as side angle side, and I'm going to do the same thing. I'm aligning my vertices. I'm going to create a triangle out of this. But again, I'm kind of restricted because these side lengths are kind of predetermined, and the angle between them is predetermined, and so that's the triangle I can make. Again, we can note that these are the same pieces. It's just in different color with different letters. But if I take these 2 side lengths and I take the angle between them and I keep that information the same in the red and blue triangle, only one triangle can actually be created. Now, again, I might have to do some reflection, I might have to do some rotation, and then some translation to bring these back to make sure they actually are congruent. But through a series of rigid transformations, even more than just 2 or 3, we can note that these are going to be congruent. And so side angle side is another one. Okay? There are more than these 2. So we can look at angle, angle, and then side. This is going to turn out to work out as well. This one's a little bit hard to see, but if I keep this angle where it is, move this down a little bit. And then A has to be somewhere on this line, but has to form a triangle, so we'll spin this around. So we have two angles in the side. This is the triangle they're able to make. Okay, so if I do that again, as you can probably predict, this is going to form the same triangle. Okay, so here, let's do a little rotation so it lines up. Okay, and again, to prove these are congruent, let's do a reflection and then a translation, and boom, they line up. So that's another one. And so again, you can play with this if you want to kind of get a sense of how this all coming together. But in the end, the thing to take away from this is that if we limit our information to the right three pieces in the right combination in the right order, then we don't actually have to use a full definition of congruency. We can use a shortcutted version of that. And so going back to the notes, okay? So going back to the notes here, that's what I mean by four shortcuts, and that's what I mean about the right three pieces of information. And so this is a representation of these. You might want to grab a highlighter that might help here, but I'm going to just kind of recover the four. And so the first shortcut, the first three pieces of information that you could use are the three sides. And we saw that um, in the demonstration just a second ago. So what this is basically saying is that if you know in two triangles, all the sides are the same, and you don't know anything about the angles, but you do know something about the sides, you can assume the angles are also the same because you can only produce one triangle out of that information. And so that's enough to assume the triangles are congruent. And so we call this the side congruence theorem. Okay, and the other four are going to kind of follow suit. Now, one thing you want to note as you're looking at this information is the order. And so for this one, we have the side, which I'm highlighting purple, that you know can run directly into this angle, and then runs directly into another side. So even though you're using two sides in an angle, this has a particular name. We call this side angle side, because just like the name, the angle is in between the sides, and in the diagram, you can see the angles in between the sides too. So this is triangle. I'm going to shortcut this a little bit. I'm going to use a congruence symbol, and that's congruence theorem. So that's two of the four. This one, we can see an angle on both that runs directly into a side that runs directly into an angle. And again, noting the order here, we have an angle that runs into a side that runs into an angle, angle into a side into an angle. And so that name is going to inform what we'll call this, which will be the angle side angle triangle congruence theorem. Which again is just a shortcut, and again what that says is as long as you show this information is true in both triangles, then you can call your triangles congruent. And so like this last one, if you note, just like the previous one, this one needs two angles in the side, but where that side is actually going to change the condition. And so we have these two angles that are kind of in a row, and then we have this side that appears outside the two angles. So unlike the previous example where the side's in between the two angles, this side is outside the two angles, and so we'll refer to this as angle, angle, side. So angle into your angle, and then into your side. And that's going to be the same over here. Angle into your angle into your side. Okay? Triangle congruence theorem. Okay? And so, I mean, if you're looking at this, once you realize three pieces is enough, just having the right combination of information is what you're going to need to prove congruency. And so that kind of changes the game for us. So hopefully that'll make sense why we're looking at like vertical angles and two lines cut by a transversal and like linear pairings and all that, because that's going to be the way that we'll find this information. That'll be the way we know sides are congruent, or we can tell angle pairs are congruent. Because if I start moving these pictures around and maybe attach them together, we'll create those situations where we can actually find those angles. Now, you can also note that these are not the only combinations of three letters I can have. There are two that I kind of left out. One was angle, 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 and the other one was side, side, angle, which I'm not going to write backwards, but I probably could. And so these turn out not to be good cases. These are actually what we call ambiguous cases, but in any way, these do not prove congruence. And the reason why is that they're not trustable. And so I'm going to go back to that this thing right here for a second. I'm going to reset this, and I'll try to quickly demonstrate how. And so I'm going to take away that side. I'm going to add three angles. So you just have these three angles kind of floating out here, and you do have to form a triangle out of it. So let's line up that guy here, swing this over to A. Okay. And then take C and put it here at the intersection, so that will help form my triangle. Here is a triangle that I can make out of that. Now the angles are going to stay the same, but I'm going to intentionally try to build a different size triangle. And so I'm going to size this here. I'll put F on this intersection. Oop, can't do that, too far. Put it here, put F on this intersection. If you look at the triangle I can create, this definitely has the same angles because I'm using the same angles, but certainly not the same size. And this has to do with the fact that it's basically enlarging. And so if you ever taken an image like off Google and you need to make it bigger or smaller, you enlarge it, but you don't change the angles of the figure. You're just changing the sides. And so that's why angle, angle, angle doesn't work. Now, angle, side, side is a little bit different. So let's go angle, B angle, and the BC. This one's a little bit weirder, and so I hope this is going to work out exactly as intended. But here's an angle. Oh, angle side side. There we go. Okay. This is going to be a little bit weirder. Let's see if we can make this work. So we have this side BC that we can't change. We have this angle B that we can't change, but this has to line up at C, and then swing up here to A. Let's move this over. And I think you guys might have caught right there why this doesn't actually work. So if I take this. Okay. So this is angle side side. So you have this angle running into a side, running into a side, but this angle here we don't know. It's not determined. And so the problem here is we can actually create two triangles. We create one here, or we can create one here with the same information. Because the B angle doesn't have a length attached to it, I'm allowed to make two, one here and one here. I'm not gonna actually create these, but you can see that that's why we call it ambiguous. Unlike side 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 or side angle side or any of the other ones that lock the information, that lock the triangle in place, this doesn't lock it in place. And so just like angle, 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 where we can get multiple triangles, we can get multiple triangles out of this as well, which is why we don't call this a triangle congruence shortcut, but instead we call this an ambiguous case. Now this will have more implications for you when you get to like algebra 2 and pre-calculus, but here are two examples where we have angle, angle, side, but two completely different triangles. And so in the end, the thing to note is that those two do not work. There's a reason why they don't work, and it has everything to do with how many triangles you can make out of the information. These sets, you can only make one triangle, so it doesn't matter where they're located, how they're twisted or positioned. If you have only three sides that are definite in both triangles, one triangle can be made. Different locations, but they're going to be congruent. Same for the rest of the shortcuts. So as you kind of flip to the back, our thinking must now shift to how we're going to actually recognize these triangles. And so just as a point on this back, the shortcuts we're talking about are side, 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 angle, angle, side, and angle, side, angle. So those are going to be the lifeblood of our work now, because if I can show that's true, I know the triangles are congruent. And so truthfully, you just have to be familiar with the relationships. Now there's a ton of angle relationships here, a ton of side relationships, but I want to review a couple of the ones we've talked about because they're going to be, your mind should be on these. And so like vertical angles are going to be one that you're just going to have to be really familiar with. Okay, so it's going to be vertical angles. Okay, that's someone you're just going to have to recognize a lot. Another one you're going to have to recognize a lot would be the reflexive property or reflection. So if you have a, let's say a shape, and they share a side, so they have this side right here that they share, I know that's going to be congruent to itself, and the reason why is a reflexive property. Okay, the reflexive property says that anything that you share, just as a review, anything that's shared is congruent. And so for this triangle, on the upper triangle, and then the lower triangle, this middle side is congruent. So like if that's what we call this, like ABCD. I can say like AC is congruent to AC because of the reflexive property. That actually justifies it. So I know that's congruent for both the green and the blue triangles. And there are other ones, and I mean, there's just tons that we need to know, like for example, like isosceles. So if we have an isosceles triangle, see in there, we know that the sides are congruent, like this guy and this guy. And if they're congruent, then we know we're dealing with an isosceles triangle. Also, those angles are congruent. And so like there are others here. I'm kind of running out of room, so like don't forget about like linear pairs. Okay, and don't forget about like two lines cut by a transversal where you have like alternate interior angles and stuff. And so like the list actually goes on and on. I can't list them all, but these are the ones that maybe you should have in the front of your mind. And so like if you're going to prove triangles are congruent using these shortcuts, I can't like give you a step by step, but I can give you some generalities. So first thing that's really important is a diagram. Okay, if you're dealing with a diagram, you need to extract information. So you need to analyze it. You need to draw it if it's not there, and you need to annotate on top of it, like write on it for the information that's important. The other thing that's really important when you're trying to like use these shortcuts to recognize them is that you have to make sure that you're analyzing properties. And when I say properties, I mean stuff that's not going to be super obvious, like stuff like this stuff. So that might not be handed to you, but if you're clever and you can see it on the diagram, that gives you more information because it's all about information extraction. The third thing you're going to have to do, like when you're kind of dealing with these things, is you're going to have to deal with the givens. Okay. Sometimes things are going to be given to you, like, hey, this is true of this object. Mark it on the diagram. And the last thing is you always have to keep the shortcuts in mind. Okay. In other words, which one am I closest to? Okay. So if I have two sides, I can almost prove things are congruent if I just had another side or another angle. And so always, always, always keep these in mind too. And so this kind of defines the task that you're going to have to do for me right now. You're going to have to try to determine if you have a couple triangles, are they congruent? We're not going to probably do it by the full definition, but we are going to do it possibly by some of these shortcuts. And so the question is, if I give you a diagram, can you prove they're congruent by locating this shortcut within that diagram? We're going to stop the notes here, okay? So this is a point where you need to get the worksheet from the substitute. There should be two of them that you're going to get this exact practice. Now the key is attached, but to give you a sense of what I mean, if I take like this one right here, you can note that right now these two triangles, which are unnamed, have two angles that are congruent to two angles. Now to prove this is congruent, I need more information, so I have to use what I know. I have to use what I know about properties and such to actually find more information. And so for like this one in particular, we can note that we have like this middle side that's shared in both triangles. Well, if we have this middle side that's shared in both triangles, we have angle, side, angle. Okay? So these are congruent because if we use a reflexive property, that tells us this middle side is congruent to itself, thus providing us angle, side, angle in both triangles. I can't write on this, I don't think. I'm trying to. It's not letting me. So anyway, this side right here can be marked to be congruent. You just have to stay sharp like that. And so like, for example, this one, we can note that we have an angle and side in both these shapes, which is really close to some triangle congruency shortcuts. But if we notice here, we have vertical angles right here, and again, I'm sorry I can't mark them, but if we have these vertical angles, then we actually complete angle, side, angle, and then we know the triangles have to be congruent. If we don't have all the information, shortcuts have to suffice. Okay, so that's going to have you practice today. I know there'll probably be some questions, so do your best on the worksheets, just like always. Check your answers in the back on the keys. Be prepared to ask me questions on Tuesday when we meet again, because that's when we'll roll full steam on this. If you want to kind of get a sense of where this is going, all you really have to do is go to your notes and look at the next question. And while I'm not requiring you to do this right now, this can certainly give you a sense why I'm having you do this practice in the first place. So if I want to prove these triangles are congruent, and remember the word prove comes with some very specific ideas, we're probably going to do this by meeting a shortcut. Well, if you realize this is isosceles, you might know something like this. If you see this line in the middle as reflection, you might notice that's going to be congruent as well. And so if looking at these two triangles and wanting to prove them congruent, it looks like we actually have met one of the shortcuts. Okay? Because if you can notice in both triangles, we have a side that runs into an angle that runs into a side. These triangles would have to be congruent because of the side angle side shortcut. All right. So we'll talk about this last problem more in depth on Tuesday. For right now, do your best with the worksheets. Try to recognize these triangle congruency shortcuts in the diagrams that you have. Please use stuff like vertical, reflexive property, two lines cut by transversal, definition of bisector to help you find the information that you don't currently have. Okay. So work hard, do well. I'll see you guys next week. Thanks.